From weather forecasting to human genome mapping, from curing the world's deadliest diseases to designing more energy-efficient materials, high-performance computing touches every part of our lives. The industry and world nations recognize the strategic importance for HPC and AI to drive competitiveness, progress, and security, bringing scientific computing demand to new heights. Hi, I'm Jeff. I'm honored to represent the thousands of engineers working on Intel's HPC and AI technologies and products. Our group's mission, much like the HPC communities, is to help solve the world's most challenging problems faster, and to do it in a sustainable manner by achieving results while using less energy. It's a lofty goal that requires us to push the limits of technology and our innovation. Sometimes we achieve our goals, and other times we fall short. Regardless of the obstacles we face, we will always keep striving to help you, to help the world. There is incredible diversity in traditional HPC codes, and these continue to evolve and advance with the integration of AI-based techniques. If you look at common workloads by vertical and characteristics, you'll see some are in-memory bound, others are compute bound, some have small kernels with a lot of control flow, others have large data parallel kernels, and most require extremely large data sets. There's no one-size-fits-all solution. Just like there are often multiple routes to reach the summit of a mountain, the industry has approached this diversity with multiple architectural routes. Route number one increases CPU core count and enhances those cores with new instructions and integrated acceleration engines. This enables high reuse of existing code and leverages large system memory. Route number two utilizes discrete GPUs to offload data parallel kernels. This leverages the data parallel compute on GPU and the attached high bandwidth memory. Is the CPU or the GPU route the best one? Yes, but each route has its pitfalls. Over the last decade, peak compute has increased along the CPU route significantly, but workload performance hasn't kept up because we haven't been feeding the cores efficiently with data. This imbalance has been a major obstacle, leading to wasted cycles, wasted energy, and wasted costs. This is like building your muscles to get to the top of a mountain, but not improving your cardiovascular system to supply that muscle with oxygen. Along the GPU route, we've had to deal with a substantial obstacle of porting and refactoring code. This has been further hampered by proprietary GPU programming environments that prohibit portability between GPU vendors and inconsistency between CPU and GPU implementations. Fundamentally, CPUs have been stuck with too little memory bandwidth, while GPUs have too little memory capacity, and moving data between the two results in lost performance and wasted energy from data movement overhead. We want GPU-level memory bandwidth at scale for the majority of HPC codes that run on CPUs, while also making it easy to share code investment between CPU and GPU for those workloads. To ensure no HPC workload is left behind, we need a solution that maximizes bandwidth, maximizes compute, maximizes developer productivity, and ultimately maximizes impact. That's why I am excited to introduce the Intel Max Series product family, which includes the Intel Xeon CPU Max Series that supercharges the Xeon architecture with high bandwidth memory, and the Intel Data Center GPU Max Series that is our highest performing, highest density, general purpose discrete compute accelerators. The entire Max Series family of products are unified by one API for a common, open programming model to unleash productivity and performance. Let's dive into the products. Xeon has been the foundation for HPC deployments with billions of lines of optimized code. Xeon Max integrates high bandwidth memory to the 4th gen Xeon scalable processors, codenamed Sapphire Rapids, that's now in production. Xeon Max includes up to 56 performance cores constructed of 4 tiles. The tiles are connected together using Intel's embedded multi-die interconnect bridge technology, which is a low latency interconnect that provides full mesh bandwidth. Xeon Max also includes PCI Express Gen 5 and CXL 1.1. We weren't the first to integrate HBM into an HPC-oriented CPU, so let's hear the initial pioneer on the importance of this new innovation. The Xeon Max CPU is the first and only x86 processor that supports high bandwidth memory. With 4 stacks of HBM2E and 64 gigabytes of ultra-high bandwidth in-package memory, the performance implications for memory-bound applications are truly astounding. Each tile is connected to a dedicated stack of 16 gigabytes of HBM memory. At the highest core count, this means that Xeon Max CPU provides 1.14 gigabytes of HBM capacity per core, enough capacity to fit a large percentage of the most popular workloads. The Xeon Max CPU is designed to be used in 3 memory configurations: HBM only, flat, and cache. HBM and cache modes can be run seamlessly with no code changes. Now, power is a major limiter for large data center deployments, especially now. So it's critically important that we develop higher performing hardware within the same power and thermal budgets. A Xeon Max configuration without DIMMs consumes 68% less power than an equivalent performing Milan X system. Kyoto University is one of the early customers for the Xeon Max CPU. Its high bandwidth memory will help theoretical physicists uncover the nature of the universe. The specs and features are great, but what gets me most excited is the performance we're seeing on a breadth of applications on Xeon Max. First, industry standard benchmarks, over 5x generational gains and versus the competition. Now, looking at real-world workloads, we have gains ranging from 60% improvement to over 300% improvement. These come with substantial performance per watt gains as well. Now let's dive into a few specific verticals and see the impact of Xeon Max CPU. Manufacturers use HPC and AI at nearly every stage of product development, from design to automation to visualization. Altair is a longtime Intel customer who offers engineers tools like AccuSolve to quickly calculate fluid or thermal effects of a design change. The HQ model is a large AccuSolve benchmark with over 6 million nodes and 200 elements in the model. Xeon Max shows significant performance improvement. The CPU cores and threads that were starved for data using DDR memory are now fully fed by the HBM stacks and can compute more efficiently. Improved performance per node will give customers faster turnaround for product development and analysis. And we're truly excited to partner with Altair to bring additional value to their customers. Molecular dynamics is a key domain for HPC practitioners. High accuracy computational methods, such as DFT, can be very expensive and impractical. To alleviate this, researchers are applying deep learning in conjunction with compute-bound applications such as LAMPs to reduce the time to solution while maintaining the same or similar accuracy. DeepMD is one of the deep learning workloads enabled on Xeon Max. With 3 times the training power and 135 times the inference speeds, we can accelerate the time to solution for molecular dynamics. Another great test for Xeon Max CPU is Earth system modeling, because the Earth is big, especially when you split it into small meshes and solve complex physics at every point. The model for prediction across scales is a climate modeling framework developed by Los Alamos National Laboratory and NCAR. Using the 60-kilometer resolution model running on a Xeon Max, we achieve faster performance compared to Milan X. And you can get this performance out of the box without any code change. Our end customers are enabled by OEMs and solution providers like HPE. I'd like to invite HPE to talk about their Xeon Max-based projects.
At HPE, we are proud to offer an industry-leading end-to-end supercomputing portfolio for both the enterprise and public sector. We understand that competing in this exascale era means that more organizations of all sizes must process vast amounts of data faster than ever before to support new modeling, simulation, and analysis on an unprecedented scale. Our new HPE Cray EX and HPE Cray XD supercomputing systems support the Intel Xeon CPU Max series. We see the Xeon Max series as a compelling technology for superior application performance, enabling us to bring powerful solutions to market that will help customers unlock new business value and adaptive insights in verticals like health and life sciences, oil and gas, and national labs. Recently, HPE delivered a significant HPE Cray solution with fourth generation Intel Xeon scalable processors for the Los Alamos National Laboratory's new supercomputer Crossroads. HPE will ship the Xeon Max series for the second phase, which will support the laboratory's stewardship of the U.S. nuclear stockpile and other nuclear security missions. From national defense to climate prediction to healthcare, supercomputing impacts our daily lives in so many ways, and I can't wait to see what our customers do to create a better world now and the years to come. Thank you.
Thank you, Trish.
We also have more than 30 system designs with the Xeon Max from industry-leading solution providers. Now, we've significantly improved that CPU route by addressing the memory bandwidth problem on CPUs. But on the GPU route, we still have the problem of how do you develop software and do so in an open environment. Intel is committed to open platforms and industry-defining standards. Our customers and developers can't afford to be locked into a single vendor or compute architecture. We must embrace the entire range of architectures and make them work seamlessly together. Let's look how we do that. OneAPI is an open, standards-based, unified programming model that lets you utilize the entire platform with a single code base and software stack. While Intel started OneAPI, it's now a thriving ecosystem. There are 29 centers of excellence. The core language and libraries are available across a variety of architectures with toolkits for domain-specific optimizations and tools for analysis and rapid porting. Now let's look at how we can leverage OneAPI to accelerate and solve the obstacles of the GPU route. For that, I present the Intel Data Center GPU Max series. The first version in the Max series GPU product line, codenamed Ponte Vecchio, packs over 100 billion transistors into a single package and contains up to 128 Xe HPC cores, Intel's foundational GPU compute building block. The Intel Xe-Link high-speed, coherent, unified fabric offers flexibility to any form factor to enable scale up and scale out. The Max series GPU also includes up to 128 gigabytes of high bandwidth memory, 408 megabytes of L2 cache based on discrete SRAM technology codenamed Rambo cache, and 64 megabytes of L1 cache. The attention to detail in the memory hierarchy with high capacity and bandwidth is all in service of delivering realized workload performance. Beyond memory, another great feature of the Max series GPU is Intel Xe matrix extensions. Each XMX engine is built with 8 deep systolic arrays, enabling vector and matrix capabilities in a single device, dramatically speeding up AI training and inference. Science is about more than just calculating results. It requires visualization to iterate, learn, and improve. When simulations are generated on the GPU, you want to visualize the results there as well. That's why we incorporated up to 128 ray tracing units onto each Max series GPU, which makes it a premier product for scientific visualization and high-performance animation as illustrated with this eye candy.
I'd like to invite Scott from Lenovo to share a few words.
Hello, everyone. I'm Scott Tees with Lenovo, and we are super excited to be joining Intel for Intel's SC22 Keynote, but we're even more excited to be one of the first partners to be providing the new Max series GPUs to our customers. Lenovo and Intel have been working on these products for quite some time as part of our long-standing partnership. Now the products are getting ready to ship. We're excited to see the strong performance and also the strong global demand. Customers today are looking for maximum performance, but they also want to know that the IT they choose is delivering the best performance per watt in the most sustainable approach possible. That's why we're so excited that the Max series CPUs and GPUs are being added to the Lenovo Neptune family of liquid-cooled offerings. These products help users use liquid cooling to deliver the highest performance, highest density, and lowest power consumption possible, making high performance more sustainable. Now, I want to thank Intel for their continued partnership helping us deliver these amazing products. For those of you that are going to be joining us in Dallas for SC22, I want to invite you to stop by the Lenovo booth to check out how these Max GPUs will look inside of our systems. The new systems are going to allow users of all sizes across all industries to build supercomputers capable of tackling humanity's or business' greatest challenges. So with that, thank you, Jeff, and back to you.
Our engineers and external developers have been busy porting codes from proprietary GPU implementations to the Max series GPU. Here are dozens of codes that are running well on Max series GPUs today. We continue to tune performance with a focus on productive offload. Through the beauty of one API, these ports will serve the entire HPC community regardless of what architecture or vendor you use. Let's look at a few specific examples of how the software effort helps unleash performance. OpenMC is a community-developed Monte Carlo particle transport code for exascale computations. On the Max series GPU, we sustain nearly 1 million particles per second using OpenMP target offload. This is a 2x performance gain over NVIDIA's A100. NextRS is an open source Navier-Stokes solver based on the spectral element method targeting classical processors and accelerators like GPUs. The Max series GPU with SYCL implementation shows significant performance over the A100. We'll be offering the Max series GPU in several form factors to address different customer needs. The Max GPU 1100 is a 300-watt double-wide PCI Express card with 56 XE cores. Multiple cards can be connected together via XE-Link bridges. This is the perfect solution for individual developers to harness the power of Max GPUs in mainstream servers and workstations. The Max GPU 1350 is a 450-watt OAM module with 112 XE cores and 96 gigabytes of HBM2E memory. In addition to the Max GPU 1350, we plan to offer a version with lower I/O bandwidth to meet the needs of different markets. The Max GPU 1550 is our maximum performance 600-watt OAM module with 128 XE cores and 128 gigabytes of HBM. These variants address high-density systems with liquid cooling infrastructure. Beyond the individual cards and modules, we will offer modular subsystems with by-4 GPU OAM carrier board with XE links built in to enable high-performance multi-GPU communication within the subsystem. The by-4 subsystem supports both 450 and 600-watt OAM SKUs with up to 512 gigabytes of HBM2E memory, giving us an amazing bandwidth of 12.8 terabytes per second. Imagine the possibilities with multiple subsystems in a single server. Let me introduce Dell to say a few words about what we're doing together with the Max series product family.
Thanks, Jeff. You know, Dell and Intel have been collaborators in the HPC and AI space for a long time now, and it's really exciting to see all of the new technologies and new solutions that we're going to be working on together. You know, we've collaborated with customers like the Frontera project at the Texas Advanced Computing Center. We've collaborated on the CTS2 cluster at Lawrence Livermore National Labs. And you know, now we're getting the opportunity to work with you in a whole new area with the Intel Max series GPUs and providing that GPU compute power in our solutions for our customers as we move forward into new areas in AI and high performance computing. Really looking forward to doing that. As a matter of fact, we've got a new solution, a new server, Power Edge server, coming up at Supercompute. Can't say too much about it today, but definitely look for it next week.
I can't wait to see more at SC22. We have more than 15 system designs from industry-leading solution providers that will deploy in 2023. The Max series product family provides you with a complete platform solution. All the performance results you have seen for Max GPU were with Xeon as the host. Let's take a look at the benefit provided by the combination of Max CPU and Max GPU. Performance for the classical molecular dynamics code lamps running the liquid crystal workload is baselined on the top-end Milan X CPU. we see substantial gains on both third and fourth generation Xeon scalable processors in 2-socket configurations with DDR. Xeon Max with HBM delivers another significant jump. Then we add 6 Max GPUs on the node and we see almost a 10x leap. You can truly maximize performance with the Intel Max series. This year, we have focused our execution on the large deployment for the Aurora supercomputer, which utilizes the entire Max series portfolio. Let me introduce Rick Stevens, Argonne Associate Laboratory Director, to give you the status of Aurora.
Thanks, Jeff. So Aurora is a very large and complex system with over 10,000 compute nodes, and those nodes are currently being installed. We're installing nodes essentially every day. It'll take several months to continue building that out. We've also built the network infrastructure that will allow these nodes to communicate, to turn the system into a single computational engine that can solve large-scale problems. So it takes many, many months to stand up these supercomputers and then to validate them and to commission them. And so we're in the middle of that process now with Aurora. So as we build these large-scale systems, we also build smaller test and development systems that help us debug software and prepare the user community for the large-scale system. Our test and development system is called Sunspot. It'll be 128 computational nodes comprising 768 of Intel's Max series GPUs, the new GPUs that we're building Aurora out of. And it will also have a fast network that connects these nodes together. So that system will be the first system that users will have access to as they begin porting their codes towards Aurora. And that system will be online in the next couple of weeks. So our early evaluation of our pre-production hardware is showing quite competitive performance to systems that are currently available in the market, both at the component level, at the individual GPU and CPU level, but also at the architectural level of the whole system. We expect the production hardware to be even better, and we look forward to having the ability to test this at scale across the entire system. The Aurora plan is to run a system called DAOS. DAOS stands for Distributed Asynchronous Object Store. It's a type of storage system that's very high performance, that will run across all of our storage nodes, that provides very high bandwidth I/O to all of the compute nodes. It's a product that we're very excited about pioneering at large scale, and you'll hear more about it next. Back to you, Jeff.
Thank you so much, Rick. It's great to see the progress and see how it's already helping to solve key scientific problems. As Rick mentioned, DAOS is a foundational technology used in Aurora. I can't overstate its importance, as feeding compute isn't just about memory bandwidth, but also about the latency and bandwidth to distributed storage. Using just 200 storage servers on Aurora, DAOS broke the bar of 6 tebibyte per second of bandwidth, more than 2x higher than any system on the IO 500 list today. And the full Aurora system will have more than 5x this number of storage servers. We're very excited and looking forward to seeing the results of this year's IO 500 list at SC22. The Intel Max series and the long road to get here signals Intel's dedication to the HPC and AI market. Since we want to keep climbing the performance hill, I like to share updates to our multi-year Max series roadmap. Rialto Bridge is the next product in the GPU line, also available in PCI Express card, OAM, and subsystem form factors. Rialto Bridge will support up to 160 Xe cores and an 800-watt OAM 2.0 module. After Rialto Bridge, we will bring to you a revolutionary architecture codenamed Falcon Shores. This will represent the convergence of the CPU and GPU routes to address our obstacles related to sharing and moving data between architectures. Falcon Shores XPU will bring x86 and Xe GPU acceleration together. Products like Falcon Shores will accelerate the convergence of HPC and AI and also bring greater energy efficiency and sustainability to the data center. We expect Falcon Shores to deliver significant performance per watt, compute density, and memory capacity and bandwidth, all in a single socket with a vastly simplified GPU programming model. The Falcon Shores architecture also enables flexibility to integrate new IP both from Intel and you. You can imagine future incarnations with multiple different IPs to bring new capabilities to the table, manufactured utilizing our IDM 2.0 model. This is the journey we are embarking on. Customers are asking for this, and we need to build an architecture and deployment to enable the future of HPC. A general purpose solution is good but not sufficient. As more customizations are required, Falcon Shores will serve as foundational architecture for customer solutions at scale and with a rapid deployment cadence. We've covered a lot of ground today. It's been a long journey with many obstacles that we've had to jointly overcome. As we continue to push the envelope, I want to thank the industry for your partnership and for pushing us to new heights. The Max Series product line of CPUs and GPUs and One API are ready for your most demanding HPC and AI codes. I can't wait to see how you'll use them to realize our shared goal of solving the world's most challenging problems faster. Thank you so much.